What if your neural network could grow to trillions of parameters, yet only use a tiny fraction of them for any single task?
That's exactly the core idea of mixture of experts. It enables models to scale to outrageously large sizes, a term coined by the original paper, while maintaining efficient inference.
Massive size sounds powerful, but usually that implies massive computation, too. How do they achieve that?
The key lies in something called conditional computation. The network only activates parts of itself as needed for each specific input.
The authors of this foundational paper, Outrageously Large Neural Networks, explain it directly. The capacity of a neural network to absorb information is limited by its number of parameters.
So more parameters mean more information capacity, which makes sense. But the computational cost has always been the bottleneck.
Their solution was to introduce a sparsely gated mixture of experts layer. This isn't just one big network, it's many smaller ones.
A mixture suggests multiple pieces, but sparsely gated sounds like only some are active. How does that work together?
Imagine a room with hundreds of specialist doctors, but for each patient, only one or two specific doctors are called in. That's the core idea.
So the patient's symptoms determine which doctors are needed, not all of them attending every case. That's efficient. This analogy is useful for understanding conditional activation, but remember that in MoEs, a patient, a token, isn't diagnosed by a single human doctor. The network processes the input, and the diagnosis, routing decision, is made by a mathematical function, not human intuition, and can involve multiple doctors, experts, simultaneously.
A trainable gating network determines a sparse combination of these experts to use for each example. Specifically, this gating network is itself a small neural network, often a simple linear layer followed by a nonlinearity that takes the token's representation as input and outputs a score for each expert.
A gating network sounds like a traffic cop directing tokens to the right specialist. And it's trainable, not hard-coded?
Precisely. This allows for immense scale. By only activating a fraction of the total parameters, you can have greater than 1000x improvements in model capacity, meaning the total number of distinct parameters available for learning is 1000x higher, without a proportional increase in computation per token, because only a small fixed number of experts are ever used for any given input.
1,000 times. That represents a substantial increase in what a neural network can potentially learn and store.
They applied MoEs to language modeling and machine translation, tasks where absorbing vast quantities of knowledge is critical.
Which makes perfect sense. If you want to understand all human language, you need an enormous amount of capacity.
The results were notable, significantly better results than state-of-the-art at lower computational cost, implying higher accuracy or perplexity at a lower computational cost per inference.
So, better and cheaper to run, not just bigger. That's the real breakthrough.
This original paper laid the groundwork. Now, let's dig into how this gating network actually decides which experts to pick.
I'm still wondering how these specialists or experts are structured and how the traffic cop learns to direct the flow.
Building on the idea of conditional computation, the core components of an MoE are simple: many experts and one router.
So the router is that trainable gating network we just heard about, and the experts are the subnetworks.
Yes, in transformers, sparse MoE layers are used instead of dense feed-forward network, FFN, layers. Each expert is a neural network, often an FFN.
So these MoE layers directly replace the standard FFNs inside a transformer's architecture, making them modular.
Think of it like a library. A dense model has one giant comprehensive book covering everything.
An MoE has many specialized books.
And instead of reading the whole giant book, a smart librarian, the router, directs you to the specific chapters or books you need. However, unlike a librarian who needs to physically fetch books, the router in MoEs mathematically combines the outputs of chosen experts, rather than simply pointing to one.
The blog post visualizes this: a gate network or router that determines which tokens are sent to which expert. To be precise, for each token, the router computes a score for every available expert. Then, it uses these scores to decide which experts will process that token. This happens for every single token.
Every token decides its own path, so a token for cat might go to an expert on animals, while walk goes to an expert on verbs.
That's a good intuition, but here's where the analogy breaks slightly. It's not always one-to-one. We can send a token to more than one expert.
So the librarian might suggest 2 books or parts of 2 books if the query is complex or ambiguous, not strictly mutually exclusive.
The article emphasizes the router's role. The router is composed of learned parameters and is pre-trained at the same time as the rest of the network.
This is crucial. The routing isn't hand-engineered. The network learns how to route. That's powerful.
This sparsity is what allows the massive scaling. The blog states, conditional computation allows one to scale the size of the model without increasing the computation.
So the reason we get huge models that are still fast is because we're only activating a small subset of the total parameters at any given time.
The benefits are clear. MoEs are pre-trained much faster versus dense models because the computational cost for processing each token remains relatively constant, tied to the number of active experts, K, even as the total number of available parameters scales up dramatically. They also have faster inference compared to a model with the same number of parameters for the same reason. Only a subset of parameters is active per token.
Faster pre-training and faster inference. This offers significant advantages, allowing models to learn more and respond quicker.
But there's a trade-off. Require high VRAM as all experts are loaded in memory. Even if not all are active, they still need to be present.
So while computation is sparse, the memory footprint is still for the full, outrageously large model. That's an important distinction.
This brings us to the actual mechanisms. How does this router make decisions, and how do we ensure it uses all our experts effectively?
I'm especially curious about how it learns to route without some experts hogging all the work.
The simplest gating function uses a standard neural network, like a linear layer followed by a softmax. This assigns a probability or weight to each expert. If you then feed the token's information, weighted by these probabilities, to all experts and sum their outputs, that's a dense mixture. The key to sparsity is to then only pick a few experts based on these scores.
If it runs all experts, where does the sparsity come from? That sounds like a dense model with extra steps.
That's where Shazir's work comes in, introducing noisy top K gating. After computing initial expert scores, e.g. from a linear layer, this approach adds a small, trainable amount of random noise to these scores. Then it explicitly selects only the top K experts based on these noisy scores. So instead of just a weighted average of all experts, we explicitly select only a few, enforcing that sparsity. If K is 2, for example, the gating network computes scores for all experts, adds a small, trainable amount of random noise to these scores, and then selects only the 2 experts with the highest noisy scores to process the token. The outputs of these chosen experts are then combined, typically by weighting them with their original pre-noise gating scores and summing them. So, even if an expert has a small weight,
It's discarded if it's not in the top k. This is how the computation gets sparse.
Why the noise? Is it just to make the routing less deterministic, or does it serve a deeper purpose?
The article explains, why do we add noise? That's for load balancing. It helps prevent the router from always picking the same few experts.
Without load balancing, the gating network converges to mostly activate the same few experts. This is inefficient and underutilizes capacity.
So, without intervention, a few experts become superstars, and the others sit idle, defeating the purpose of a mixture.
Imagine our specialist doctors again. If the receptionist always sends everyone to the two most popular doctors, the others don't gain experience.
And eventually, the popular doctors get overwhelmed, and the less popular ones remain untrained and underutilized. That makes sense.
To fix this, an auxiliary loss is added to encourage giving all experts equal importance. This loss actively pushes the router to distribute tokens.
So, during training, the model is penalized if it doesn't spread the tokens around. It's a built-in incentive for fair distribution.
This careful load balancing was crucial for models like G-Shard, which explores scaling up transformers beyond 600 billion parameters. Without it, the massive scale simply wouldn't be effective.
So MoEs aren't just about big numbers. They're about smart management to make those big numbers work in practice.